Welcome to this explainer. Today we're going on a wild ride, tracking the incredible journey of a single sound wave. We'll follow it right from its violent microscopic birth, through the physical world around us, all the way to its invisible echoes. Sound is such an everyday thing for us, right? But the actual mechanics of how a simple rustle of leaves or a huge clap of thunder manages to reach our brains, it is honestly so elegant and fascinating.
So let's kick things off with a bit of a mystery. Picture this. You got two astronauts floating outside a space station, working together to repair a massive metal arm. Can they actually hear the clanking of their tools, or even each other's voices out there in the vacuum of space? Now, if you watch a lot of sci-fi movies, you probably have a guess. But today, we're diving into the hard science to find out if space is a loud construction zone or just a completely silent void.
To solve that spacewalk mystery, we have to start at the very beginning. Section 1. How sound is born.
Think about stretching a rubber band across an empty cardboard box. You pluck it, and what happens? You hear a twang, sure, but you also see the band physically blurring back and forth. Now just watch it. The absolute second that rubber band stops moving, the sound vanishes too. Actually, you can try this right now. Gently place your hand on your throat and say something out loud. You'll literally feel the tightly stretched flaps of your vocal cords buzzing. That right there is the singular origin of every sound you've ever heard.
And that perfectly brings us to our first core concept. Sound is exclusively produced by vibrations. It's just that periodic back and forth motion of an object. So whether it's a tuning fork sending ripples through your coffee cup, your vocal cords shaping words, or a really annoying mosquito buzzing by your ear, every single sound starts with something physically vibrating.
But once that vibration happens, our sound wave needs a road to travel on. It can't just magically teleport to your ear. Which brings us to Section 2, traveling through a medium.
Here's where things get really interesting. Imagine a ringing electric bell sitting inside a sealed glass jar. At first, you hear it loud and clear. But if you hook up a pump and start sucking all the air out of that jar to create a vacuum, the ringing gets fainter and fainter until total silence. Even though you can still see the little bell's hammer whacking away. And just like that, our spacewalk mystery is solved. Those astronauts, they hear absolutely nothing.
The huge takeaway here is that sound absolutely cannot travel through a vacuum. It desperately needs a material medium to move through, so solids, liquids, or gases. But here's the real secret. It's the energy that's traveling, not the physical stuff itself. When you talk to a friend across the room, the air molecules from your mouth aren't flying into their ear. It's more like a line of dominoes. The particles just bump into their neighbors, passing the energy down the line, while barely moving from their original spots.
Let's zoom way in to see what that actually looks like in Section 3, Anatomy of a Wave. Picture a vibrating object, let's say a piston in a tube, shoving forward. As it pushes out, it violently squishes the air particles right in front of it together. This creates what we call a compression. It's basically a high-pressure, high-density traffic jam of air molecules. And that dense little zone bumps into the air next to it, passing the squeeze forward.
But remember, the object is vibrating, so it doesn't just push, it sharply pulls back too. When it retreats, it leaves behind an empty gap. We call this a rarefaction. It's a low-pressure, low-density pocket where the air particles are spread really far apart.
If you've ever stretched a metal slinky across the floor and gave it a quick push, you've seen this exact thing happen. A sound wave is really just a rhythmic, traveling dance of those bunched-up compressions and stretched-out rarefactions. Now, if we map that out on a graph, the squished, high-density compressions become the peaks, or crests, and those spread-out rarefactions become the dips, or troughs.
Now, this is crucial. Light travels in transverse waves where things vibrate up and down, kind of like people doing the wave at a stadium. But sound? Sound is a longitudinal wave. That means the particles are shaking back and forth perfectly parallel to the direction the wave is actually traveling. They're pushing and pulling in the exact same direction the energy is flowing.
All right, so we know how it moves. Now let's see how that translates into what we actually hear in Section 4, speed, pitch, and loudness.
You might not know this, but sound is an absolute speed demon when it travels through solid metal. In the normal air around us, sound moves at a pretty decent 340 meters per second. In water, it speeds up to about 1,500 meters per second. But in solid steel, it rockets through at a staggering 5,000 meters per second. If someone bangs on a long steel fence, that sound is going to blast through the metal and reach your ear roughly 15 times faster than the exact same sound traveling through the air. Crazy, right?
As for what we actually hear, the pitch of a sound is entirely dictated by its frequency. That just means how many of those wave compressions are smacking in your eardrum every single second. High frequencies mean super short wavelengths, which gives us the shrill, high pitch of a dog whistle. On the flip side, low frequencies have long, stretched-out wavelengths, giving us the deep, booming rumble of distant thunder.
So what happens when our traveling sound wave hits a literal brick wall? Let's check out Section 5, the science of echoes.
Believe it or not, there's a strict biological speed limit for echoes. For your brain to register a clear, distinct echo, instead of just a muddy, drawn-out reverberation, that reflected sound wave needs to take at least 0.1 seconds to bounce back to your ears. If it hits you faster than 1/10 of a second, your brain simply mashes the original sound and the reflection altogether.
And since we already know the speed of sound in air is 340 meters per second, we can just do the math. 1/10 of a second means the sound travels 34 meters. Cut that in half because the wave has to go out to the wall and come back, and you get 17 meters. So to hear a genuine, crisp echo, you have to be standing a minimum of 17 meters away from a hard surface.
Finally, let's wrap things up with Section 6, Beyond Human Hearing, where things get a little invisible.
You see, human hearing is actually pretty limited. We only pick up frequencies between 20 Hz and 20,000 Hz. Anything outside of that tight little window is completely invisible to us. But there is a massive, silent symphony playing out all around us. Frequencies below 20 Hz are infrasonic. These are the deep, powerful rumbles elephants use to talk to each other miles away. And above 20,000 Hz, those are ultrasonic waves, the super high-pitched squeaks bats and dolphins use to navigate using echolocation.
But human ingenuity is wild. We've actually figured out how to harness those completely undetectable ultrasonic waves for our own technology. Submarines use them as sonar to map the pitch-black ocean floor. Doctors use them for ultrasonography to safely look at internal organs without ever picking up a scalpel. We can even focus high-intensity ultrasonic waves to literally shatter kidney stones right inside the human body. It's basically a medical superpower. As we wrap up this explainer, I want to leave you with this thought. Right now, scientists are using ultra-sensitive microphones to listen to the ultrasonic crackling of microbes in our soil, and space probes are beaming back the eerie acoustic hums of the Martian wind. If sound waves can travel through basically any physical medium anywhere in the universe, what other invisible secrets vibrating just slightly outside of our human frequency range are waiting to be heard?